everybody. My name is Dragan Rakita. I work on Paradigm on Rust Ethereum. I am author of Rust EVM, very fast EVM implementation. And today I'm talking about paths to the faster EVM. Sorry, this works. We'll start with interpreter loop. Basically, it's the main loop that every instruction basically needs to be executed. It's the hot loop that a lot of optimization can be done. Basically, most of them are obvious. Some of them are needed years to figure out. Not just figure out, but to get idea that it can be done. But it's always nice to just list few of them, just to see from where we came and where we are now. For example, padding the bytecode. So EVM bytecode can end at any place. That means previously, if you want to iterate bytecodes, you needed to check the length of the bytecode. This is very easily mitigated just with padding zeros. So if you are padding the bytecode, and you can assume that your bytecode is always going to end with stop. So your loop is very simple. One of the things is using for the gas calculation, using native unsigned 64, previously from OpenEthereum. I worked on OpenEthereum a little bit. They had generic over unsigned 64 to big number. And it's I think everybody now uses native. It's a lot easier, a lot smaller calculations. Removing jump table pass. This was one of the things that we stumbled about when the foundry started using RAM. They started profiling it. And most of the fuzzing was spent on basically calculating jump table. Jump table is needed so that when you do any jump inside EVM, so that you know where the jump destination are. The problem with that is with the push, you have arbitrary bytes inside. Hopefully this is going to be fixed in Ethereum object format. It's going to be fixed in Ethereum object format, not probably. And idea there was, why not save jump table, calculate only once, and just reuse it. Even in ret, we are basically saving jump table as the list of bits inside the database. So we are skipping that part. Yeah, because if you don't skip, it's iterating bytecode 2 times, one for analysis, second time is for execution. Not that great. Gas block and stack limit requirement, something that EVM1 implemented. Basically, if you have list of opcodes that you know that are going to be executed, you can pre-calculate gas, and you can pre-calculate how much stack items it needs, so you can basically do gas calculation smaller number of times. The things that are not that impactful, basically that are not giving that much of performance. Basically, we had some assumption, but yeah. Basically, any preparation for the calls, any preparation for the create are not that impactful. The idea measurement that I did is that most of the performance is spent on interpreter loop. Database fetching. Previously, when we fetched the database through the Merkle tree, that was problematic because you needed 15 fetches of database to traverse the Merkle tree. Now with flat key value database, this is not a big problem. You still need to read that and in the end commit that and to calculate state root after that. But it's not that big a problem inside EVM. 2 things that we wanted to do recently is shared memory and shared stack. That idea was assumption that we made was, hey, we don't allocate memory when we don't need it. We have some kind of memory arena where we can reuse memory or for both memory and stack. but performance impact of that was very small. And basically, in interpreter loop, using match, switch, or opcode table gained similar performance. So there was a lot of improvements on one side, and there was a lot of assumptions that we made that didn't pan out as true. In the end, what we have now, or not just RAM, but EVM in general, EVM1 was one representative EVM that's very nicely polished and very performant. We have very polished interpreter that works very nice. We already know the pain points, we already know what needed to be done, and a lot of new ideas were implemented. And with Ethereum object format, few of those things are going to be like baked in the protocol, and that's very nice. So next step for that interpreter is it is what it is. So we can transform the interpreter. What exactly is that? Now it gets interesting. Super opcodes are a good example, a good introduction to that. So there is few basically pairs, triplets of opcodes that are very frequently used. Simple idea is, hey, let's make one instruction, one opcode that's going to encompass that. Basically transform the bytecode, even not on protocol level, but customize, create new bytecode with parallel with the original bytecode, with some custom opcodes that are going to have basically custom opcodes that are going to encompass same functionality, but they're going to be a little bit faster. We still need original code so that we are compliant, but either way, idea is there. Make another bytecode. Expanding that, we can even precompile contracts. Why not? We already do that for cryptographic functions. Why don't we do that for some contracts or bytecodes that are very frequently used? Idea is the same as the ordinary precompiles, but we need to build those contracts and making them in the native language, which probably is going to be a lot faster, but it's like new code that you need to audit, you need to verify that's correctly run. And that's downside of that. Maybe for a few of them that are very frequently used, we can do that, but for all of them, it's like a lot of work. Basically, one step forward to that, let's go native. Just-in-time compiler, ahead-of-time compiler, compilation. Basically, you're not manually creating bytecodes, but you are creating automized way for your bytecodes to be created. This allows basically to use bytecode, original bytecode, transform it some way, compile it in LVM or something like that, and get the different kind of bytecode that's native. That should be faster. I first heard about that from Joachim and his work on GTVM. There are a few experiments after that, but there is no production-ready code. In the end, it seems like good research, and it seems logical. It seems that it should work, especially with the opcodes that are like in one block of the basic opcodes that are one by one, and they're not like jumps, anything jump destination between them. You know the results of that block of opcodes is going to be same. So optimizing that could be possible. EVM, Ethereum object format is introducing like static jumps, so the compilation of that should be even faster. And basically, it should allow native compilers like LVM or something like that to have more data that can compile statically. So, punchline here is we can go beyond the EVM interpreter. Idea is, hey, let's make our native code that we're going to use, and we can load that anytime. It can be dynamic library that we can use. So, one step forward. Let's talk about parallel execution. Example of that is access list, where having, access list is a good example of that. Not the best way to parallelize things because there are some problems, but the idea is what exactly are access lists? Do they contain read writes? Do they contain only touches? Do they contain storage or just accounts? Do we want to parallelize of account of the contract or storage? For example, RC20, you would like storages. And there is like introduction of the balance increment decrement that we can parallelize. Maybe we don't want to apply every like balance change, but we can like postpone it and make it more parallel. Major problems with that, with access list is dependent transaction can change your basic logic. So if you're constructing access list beforehand, you need to overcompensate for it to be even if you can, basically if there's something that's stored on the storage and something that you don't know, your transaction is going to fail. And we will increase transaction size. So the next thing is brute forcing it. Basically executing every transaction as standalone, gathering every read-write access list or list, start applying transactions one by one, and trying to find collisions. Because if you had read-write access list, you can basically check if there is collision. And if there is collision, execute transaction. First paper on that is block STM, written by DM, implemented in Aptos. Some brute force versions are implemented for Polygon and Binance, and they got like 50 to 2 times faster execution. As name applies, it's brute force way. That means if there is collision, you can expect your transaction to be re-executed multiple times. So it's a little bit wasteful. Parallel event claim. So this idea is, just imagine if you already know what transaction can be run in parallel. You have a cyclic graph where you know, hey, this transaction depends on this transaction. This information can be obtained serially, but idea is it can be even obtained externally. You can download it for somewhere else. The main idea is if you have that DAG, basically, you can execute transactions in parallel, and while you are executing, you can check if your basically claim to the parallelism is correct. That means if there is like data races or something like that, you can abandon the EVM, abandon the basically that execution, and just execute serially. Idea how that could be implemented inside the protocol, that's very far-fetched. It is years of research after this. But block builders already know some information that a lot of validators don't, that basically have transaction that they want to include. So they can execute transaction in serial and just create the DAG the best they can have. Minor balance is one of the contested addresses that is adding balance after every transaction that can possibly move at the end of block or maybe behind the last transaction, because MEV and block builders want to use that reward to bribe things. So why parallel? The question that I got here isn't the state the problem. Yeah, it is. And that's the problem that we need to focus on. But focusing on parallel is something that will come eventually. It's something that even if we don't include in the protocol, it's something that we can even reuse. A few examples are faster initial sync, basically cutting some speed on that. Faster traces, because you know dependency on some transaction, you can re-execute just subset of transaction that you need, and maybe getting shadow events, even like re-executing Walter section. One of, I took that from Twitter, adding parallelism for EVM is not about speed, but it's about enabling light clients. Basically, same thing with executing traces. You don't need to execute every intersection. So my point here is going parallel is just a matter of time. It's not priority at all now. We started some research on that in Red, but going parallel is just a matter of time. It's nice optimization and nice performance that we can get. And matter of time, I mean years and years. I think that's it. Thank you very much.